So last time we left off on talking about multi-step reactions, mechanisms, and their energies, right? And we've been talking about kinetics versus thermodynamics. Thermodynamics being the states, right? For example, the potential energy of reactants versus products. Those are thermodynamic steps, and the difference between them would be the thermodynamics, which is the reaction energy, okay? Then we also were talking about transition states, and we've actually covered transition states to some degree before a few times now. There's transition states when it comes down to conformers. There's transition states when it comes down to reactions, okay? So the highest points in an energy diagram for a reaction is going to be transition states. These are states you have to pass through to get to reactants going to products, but you also have to pass through them to get to intermediates. You'll maybe notice that you don't have the terminology yet for intermediates. That's coming right here. So intermediates are the lowest points in your energy diagram. Technically, that would also include your products, but that is labeled special because that is the end result, right, which is a product. Technically, that would also include reactants. But reactants are labeled specially because they're what you start with, right? Products are what you end with. Reactants are what you start with. The things that are the lowest points in your energy diagram that are between reactants and products, we call those intermediates, right? They're states which you can exist in and can exist in for fair amounts of time. They have stability to them. So you can actually collect intermediates at times. Though if they're high energy enough, you won't be able to. The reaction step with the highest E sub A, activation energy, will be the slowest step, and will determine the rate at which the reaction proceeds. This highest activation energy step is always the one that is your rate limiting step. It also is going to be the one that would determine like your reaction order. It's the one that determines how fast things go, okay? All right, so right here we have the energy diagram for that chlorination of methane. After doing the lecture and the homeworks, you're probably like, oh my God, no more chlorination, Dr. Clausen, please. We do that in quite a variety of ways, don't we? Yes. Okay, so if you remember, off here in the far distance, we have the initiation step, right? Okay, and that makes the chlorine split apart homolytically, so we get the chlorine atom, right? Which is the way you call a free radical chlorine, okay? That's right there then. That's one of our reactants in this energy diagram, okay? The other reactant here is the methane. So those are our reactants. They have a potential energy, which is measured right here. It's very, very difficult to actually measure a potential energy. In fact, it's almost impossible and has only been done for, I think they're up to 3 things now. Each time they do it, they have to spend tens of millions of dollars and try to calculate it out to an exact number. Okay? You can only ever get approximations typically because we're not actually that sure of what zero energy actually would be. We've never actually seen it. So, everything that we do is always energy differences. The difference in energy from reactants to products, right? The difference in energy from reactants to the rate limiting transition step. So this right here is the transition state, which would be rate limiting in this case. Why is it rate limiting? We have another activation energy over here, don't we? Okay. It's how tall of a hill you have to climb. That determines whether you're rate limiting. For example, in Wyoming, I would regularly climb a 5,000 foot height to go to school. Did it a couple times a day. Okay? What am I telling you? Well, Wyoming's up in the 5,000 feet tall height, the whole state. So I walked basically a flat surface. Well, actually, I took one hill, but it was not that big of a hill, okay? It was not a big mountain, all right? And so right here, what we see is that we're at a large height, aren't we? But this is not much of a barrier to overcome because the energy difference between the intermediates, which are right here, and this transition state, which is here, is not very high, right? So that's a fast step, okay? This right here is the slow step. It's the slowest step going from reactants to products, right? So this has the highest activation energy, and that means that's the rate limiting step. That is the transition state that is rate limiting, okay? Going from the methane with chlorine atom to this intermediates right here. Notice that intermediate is that free radical carbon that we've talked about in the propagation steps all the time. Okay, that's the slowest step. That determines things like the order of the reaction and that sort of stuff. Okay? Okay, the energy difference between these right here determines if this is endothermic or exothermic going to there. Okay? In this case, it's what? Endothermic, right? Energy went up. So that means we had to put energy in. Okay? We had to push it up the hill, didn't we? Okay. Going from the transition state to the products is what? Exothermic. We know this is thermic, by the way, endothermic, exothermic, because this says delta H, doesn't it? Okay? You can actually do the same thing with delta G's, Gibbs free energy. Do you know what you would call that? Gonic. Endogonic, exogonic. Okay? Okay, does anybody have any questions about reading this energy diagram or anything they don't understand from it? This overall reaction is what? Exothermic. It's going to give off energy, right? When we start this reaction, if we put this in an ice bath and got this really cold, would this reaction go? No, it'd go really slow at first, right? But as soon as we start it, we could put it in like an ice bath or something, couldn't we? Because it will make enough energy to power the reaction forward. How do we determine that? Look at this delta H. See how it says minus 110? That means each time we convert reactants to products, this is actually the delta H, the overall reaction, minus 105, by the way. Every time we do that, we provide enough energy to overcome the activation energy. Okay? That's what determines whether something is both exothermic and will run under its own power. Okay? And go at a good rate. This would, even if we had a very large activation energy that we could not overcome easily, this would still go, but very, very slowly. Okay? Like the gasoline in your car is slowly oxidizing right now. Okay? Or like the Grand Canyon is slowly changing. That one's millions of years, right? Or like your car is slowly rusting out into a rusted pile of junk, right? Yeah, sure, it'll take decades, but it will happen. Okay? Okay, so again, these are rates, activation energy, and temperatures. Remember that as we increase the temperature, what happens to the rate typically? Yeah, typically we would increase the rate, right? And this is because we have more of our molecules that will have the activation energy to go forward, right? Now, this is kind of an interesting thing, but hey, are all reactions exothermic? No, some of them are endothermic, right? And some of them are exothermic. And so, does anybody know what happens if you take something that gives off heat as a product and you heat it up? You can push the product into the reactants. You can push it the other way. Yeah, so if you have an equilibrium that can be established, if the reaction can run in both directions, because you have all of your products stay together, then you put the heat way up, you can actually cause it to go in the reverse direction, i.e. Le Chatelier's principle, right? Yeah. So you can actually play kind of a funny game where you make the reaction happen really fast, and you get like product when you don't have any product, and then all of a sudden you push it the other way when you start pushing products to reactants when you increase the temperature a bit more. Yeah. So like the Haber process is pretty famous for this. You need heat to start it, but once you get it started, you actually want to pull the heat out. Yeah. So, anyways, Haber process being the fertilizer, making the nitrogens for the fertilizer. This right here is some various different reactions. We can see the activation energies here. Those are going to tell you how fast things typically go. And we see right here they're directly correlated with how fast the reaction goes, isn't it? The reaction rate. When we change the temperature, what happens to the reaction rates? They increase, don't they? Yeah. Okay, so what are some of the conclusions we can draw from this? Well, with increasing activation energy, we get rate decreases. With increasing temperature, we get rate increases. Fluorine reacts explosively. See how fast fluorine reacts? That means it's going to react so fast it goes boom. Okay? Chlorine reacts at a moderate rate. Chlorine reacts in a controlled but quick manner. Okay? Bromine has to be heated to react within a timely manner. Otherwise, you'd be waiting for weeks. Okay? Iodine does not detectably react. If you tried to do this in lab, it's not going to happen. Okay? Even if you heat it, how long are you waiting? A long, long time, right? That's 10 to the negative ninth, right? Like a billion seconds for anything to happen. Do you want to wait that one? Okay. Do you want me to do an iodine reaction in one of our labs? There's a reason we don't do the iodine one, and we don't do the fluorine one either. There's definitely a reason for that. So this is a solid problem. I want you guys to start working on it. I'll give you a minute or two, and then we'll go ahead and work on it together, okay? Oh, wow, I'm off kilter today. You ever wake up from a sleep and you slept so deep that you thought you were dead? That's today for me. Like, I feel like a passenger, right? Because I only slept 3 hours yesterday and started working at like 4 or something in the morning. The sad part is I used to do this like every day, all year long. I used to just sleep 4 hours, and I've gotten lazy since I came down here in the south. Gotten southern and soft. All right. All right, so hopefully you made some pretty good progress on that. Your reaction diagram should have a place for reactants, right? And then our quote-unquote products here, okay? Okay, so it's going to be a flat line with these listed under it on which side? Yeah, your left. By the way, y'all look like you're pointing right to me. Okay. Yeah, so your left. Okay. And then, what are you going to do? Well, you're going to do a hill, right? Okay. Now, this next line that's going to have your products that are labeled under it, is that going to be higher or lower? Lower. Why is it lower? You got it. You got it. It's a negative, yes, enthalpy. It's exothermic, right? Meaning that your energy level went down. Okay? Okay. Now, so if you do this really well, you're going to try to give this some sort of proportionality to it. And so if you put whatever distance you put the first line to the second line going down as 4, how much of a hill do you want to make? About 4 times that, right? So you take that distance and 4 times up from your reactants, you're going to make your transition state, right? Why did I do that? What's my transition state height have to do with any of this? Yeah, come on. You can do it.
It shows when it's like peaking.
Yes, it shows the peaking of the energy, that being how long the reaction takes, also meaning it's the activation energy. You got it. Yeah, that's the E sub A, right? Yeah. And that's 17. That's about 4 times 4, right? Should be 16. Okay? And so what my energy diagram looks like, I can literally do it on the reaction here. I could put a line, and then I'll put a line up here. We're above this, okay? That gives you a good reference point. Okay, so above where it says following reaction, I'd put a line, and that would be my reactants, right? I'd then put a hill coming up. That's 16 going up. That's my activation energy, the difference between reactants and transition state, right? This peak here. This is then going to come down, and the line will end up down here, right? And that's -4 from my reactants. That would be my products, okay? And that difference between reactants and products, that is my enthalpy. Okay. Not bad, right? This actually shows you a real version of this. You can just look at one of these. This one right here, I believe, is actually the closest, and that's what it would look like. Okay? Okay. I just took a diagram that was close to it. This one happened to have an energy change for, that's going to come up later. Okay. So let's talk about primary, secondary, and tertiary hydrogens. If you guys started doing homework, there's actually a few questions on this. So what's a primary hydrogen? Come on. Yeah, just shoot it out, guys. First off, please do not make fun of people for being wrong in class, because that is why you're at college. Is so you can be wrong and it's like fun and funny. Because I promise you, this is basically the last time in life where you get to be wrong in a professional capacity, and it's funny. Okay? So take advantage of it. Like, just shoot stuff out just to be wrong, okay? You'll just build yourself up and get better. Yes, you do end up on a carbon with 3 hydrogens if it's primary. The real thing that makes it a primary carbon hydrogen, though, is that it's attached to a primary carbon. Okay? Any of the stuff that can't make backbone chains, oxygens, hydrogens that are just substituents, you always label those primary, secondary, tertiary based on what the carbon it is attached to. Okay? So for example, a primary hydrogen is attached to a carbon with only one other carbon attached to it, right? A secondary hydrogen is attached to a carbon with only two, exactly, two carbons attached to it. A tertiary hydrogen, called 3 degree, right, third degree, is going to be attached to a carbon with 3 other carbons attached to it. Can you have a quaternary typically? No. Yeah, you got it. Yeah, you can't have a quaternary without having some sort of charged carbon, which is very unusual and very difficult to exist. Because you wouldn't have any place to put the hydrogen, right? Carbon wants 4 bonds. Same thing with an alcohol, by the way. Alcohols can only ever have one thing attached to them. So the only way they could have a primary, secondary, tertiary terminology is by counting the number of carbons on the carbon that's attached, right? Okay. Chloride's the same way, it can only bond to one thing, right? And so you get primary, secondary, tertiary is based on the carbon, okay? Okay, this is more of a function thing. So this right here shows you 2 different situations. We have 6 primary hydrogens in this compound here, which is just propane, in case you're wondering. It's just not made in a straight chain so that we can demonstrate the hydrogens, okay? Yeah, we, tilted it. Okay, so if you look at the propane, we have 2 methyl groups. Those methyls each have 3 primary hydrogens, right? Which is a total of 6 primary hydrogens. So when we do the chlorination reaction, what ends up happening is we have a 40% chance to substitute one of those primary hydrogens. Now, that sounds impressive until you start realizing there's 6 of the damn things, right? So that means we have only a 6.6% chance of substituting each one, don't we? Okay? So the degree in likelihood of substituting a primary carbon is actually much lower than substituting something like a secondary carbon. Okay? And that's only because we have many, many primary carbons in this case, or primary hydrogens in this case, that we get a decent percentage here. Okay, if we only had one of them, we'd only have like a 6.67% chance, right? It'd be very low. Okay. Here we have 2 secondary hydrogens, don't we? Well, we have a 60% chance to substitute on the secondary hydrogen spot. Okay, to substitute the secondary carbon. And what does that mean? Well, we actually have a 30% chance per hydrogen to substitute those. So we actually had a much larger percent chance to substitute a secondary hydrogen spot. Okay? Why is that? Well, one of the things I want you to get used to is, frankly speaking, every time I say why, you can give me almost the same answer and be right about 90% of the time in all scientific subject matters. Okay? Why does anything happen ever? More stable that way. There you go. Okay? Or you can be a little bit more clever about it. It's more energetically favorable. Right? Well, why are cells the size they are? It's more energetically favorable that way. Okay? Why does it substitute on secondary carbon? It's more energetically favorable that way. Why does a rock roll down a hill? It's more energetically favorable that way. Now, the exact energies you're talking about, that can, be a little bit more tricky, right? There's only a few of them, but you actually have to think about it. But, I mean, that was true for all of them, right? It's more energetically favorable because this one's going to be more stable when we do this part of the reaction right here. And I'll show you that in just a bit, okay? But like a cell, it's more energetically favorable that way because the surface area to the volume, once you get too much volume versus surface area, you don't have the energy ability to exchange all the things the cell needs. And so the cell dies. Okay? Anyways, I've given you the cheat code now. All right. So remember your chlorination mechanism. We have our initiation step, right? Where we homolytically dissociate that chlorine. We get chlorine atoms, the free radical. The next step would be the free radical would attack the propane, and that's going to take a hydrogen from it, along with one of the electrons, leaving behind a free radical propane, right? Now we have, in this case, with propane, two choices, don't we? Notice before this, we had always done methane or ethane. In both of those cases, we never had more than one choice, did we? They're all the same hydrogens, right? All the same carbons. No difference. Now we have different carbons, don't we? Okay. So you have two options. You have your free radical is located on the primary carbon, which would be called a primary radical, right? The free radical could be located on the secondary carbon, which is the secondary radical, right? You guys starting to get how the language comes down? Okay. That's why I'm doing that, by the way. If you guys got a good grasp of it, I'll try to stop doing that at some point. But okay, so once you have your choice made here, well, that chooses everything else for you, right? So the next steps are going to be your primary radical would then attack a chlorine, elemental chlorine, right? Cl2, okay, chlorine molecule. This is then going to take one of the chlorines with one of the electrons and leave behind a free radical chlorine, right? The other option is the secondary radical does the same thing, okay? So this step's the only place where things are really different, isn't it? Okay. Otherwise, you have to think of whether this is going to be any large groups that can't access it. No, not really, okay? They're all fairly small. So the difference in stabilities, the difference in reaction rates, the difference in which one gets substituted comes down to which of these is more stable, okay? Okay, so let's go ahead and build up the case real quick. We have bond dissociation energies for our formations of various different free radicals. What we can see here is this is the methyl radical being formed, and we see that methane goes to methyl free radical. The bond dissociation energy is 439 kilojoules, isn't it? Okay. Then we do the formation of a primary radical, and that's 423 kilojoules. Anything notice something about that? Is that a bigger or smaller number? Went down a little, didn't it? Yeah, slightly smaller number, which means it takes less energy to do, doesn't it? Okay. What happened to the carbon here? Went from no substitute carbons on it to, we have a substitute carbon now, don't we? Okay. Okay, this one's the formation of the secondary radical. What we notice about the energy? Energy went down. What do we notice about the carbon substitutions? Went up, didn't it? Yeah. So what's the trend going on here? Yeah, the more substituted your free radical carbon, the less the energy, right, that you need to do that. Okay? And there's our pattern. I know, we just practiced pattern recognition. Uh-oh. Making you think again. That's awful of me. Evil, I tell you. Evil. Okay, so this is our stability order. You do not need to memorize this as long as you understand the underlying principles of it, okay? Though some of you are still going to end up memorizing it just because you're like, hell with Dr. Clausen, he doesn't tell me. Be a rebel, I guess. Okay. So the methyl free radical is going to be the least stable. Primary free radical is more stable than that. Secondary, more stable. Tertiary is the most stable, right? Okay. So again, the more substitute your free radical, the more stable they are, i.e. the less energy it takes to create that free radical, the less energy it takes to do the bond dissociation. Okay? Okay, so this is actually that energy diagram I showed you before, wasn't it? I know, right? Because that problem we did before actually was a bond dissociation energy problem. You guys notice that? We literally bond dissociated. Anyways. Okay. Yeah, so that ended up being just a bond dissociation, with the difference being we remade another one. Yeah. So it was just two bond dissociations. One to here, one to here. Okay. So anyways, right here we have the chlorine taken off the hydrogen. And what we're going to notice here is, again, these are the transition states. What do you notice about the transition state? Are those the same? They're different energies, right? Yeah. And so what does that tell you in these? Well, this is the primary up here. This is the secondary. And so when we take off that hydrogen, leave behind the free radical carbon, which is the more stable free radical carbon? Is it on the primary position or the secondary? The secondary radical is more stable, isn't it? Yeah. That's what that's showing us. Okay? If it is a lower energy barrier to overcome, what does that mean about the reaction rate? Faster, yeah. Yeah. So let's say we have a bunch of objects flowing through. So we have like water flowing around two paths. We made, a hose. One has a kink in it, goes slow. The other is a straight shot. Which one's going to move more water? Straight shot, right? So when we have a reaction going, one is slower, one's faster. Which one are we going to get more products for? The faster one normally, right? All the other things being equal, the faster one definitely, right? Okay. So the next thing we have to look at here is the product. So the products actually have an energy difference as well, don't they? Okay? And that would be a thermodynamic difference. So the primary radical product here, making that this right here with the free radical that's on the primary position, and this one right here where the secondary radical is actually on there. This has a 10 kilojoule difference, doesn't it? Okay. So you have two things going on here. The transition state is where you have the bonds partially formed, partially broken. Okay? The secondary position is more stable for having that partially formed, partially broken. And so it's going to make the secondary one faster. Okay? And then on top of that, if we let these go back and forth and stabilize to some state in the middle here, it would still choose the secondary one because the secondary free radical is more stable, right? Okay. Do you see there is a subtle difference there, but they both end up the same thing on this one. Okay? There are cases where they will be different things. Okay? So this is the more stable state. This is like looking at two pools that could exchange water. One's lower, one's higher. Which one's going to fill up more? The lower one, right? Okay. Versus looking at the speed of hoses. Okay? Which one will fill faster? Usually the one with faster hose, right? Okay. But one thing you do have to keep in mind is that the speed can be counteractive if you can go back and forth. Okay? If we can go back and forth between these states over and over and over, you'll always end up with more of the more stable form. Okay? You'll get more of the more stable product. Now, what do you notice about activation energies if you try to go backwards in this case? Is the same activation energy from the front, going from reactants to products, as it is from products to reactants? No, big difference, right? This is much more steep, isn't it? You have to get a lot more energy to go backwards, okay? And so it isn't always true that you can go back and forth in a reaction and get the most stable product, okay? Oftentimes it will be the fastest product that you make the most of, okay? And that's just because of the speed. Okay, so the tertiary hydrogen atom reacts with the chlorine-free radical about 5.5 times as fast as the primary ones. Predict the product ratios for chlorination of isobutane. That's what I had done with you before, by the way. What we did in percentages before. Okay. You can just do this one in multiples, which is a little easier. And of course, in a minute or two, I'll help you along anyway. So give it your best attempt. Whenever you're looking at multiplicals of something, what should you always put one state as? One option as? So if I say Bill Gates makes 1,000 times my salary, what would my salary be? Yeah, 1. Yeah, you just set my salary as 1, right? So, 1 college professor salary. He doesn't make 1,000 times mine. He makes like 1 billion times mine. No, he makes probably 1 million times what I make. Yeah. Hell, a lot of wealth disparity there, huh? Okay. Hell, he probably makes my salary in a couple of seconds. Okay. Everybody making good progress? All right. I think I'll go ahead and start talking about this. Okay. So there's 2 things going on here. Number 1, the tertiary position on this is going to have a reactivity that's 5.5 times the primary one, right? And so we set the primary to be reactivity of 1. The tertiary would be reactivity 5.5, right? Okay. Now the other thing we have to look at if we're going to look at the product ratios is how many hydrogens can be on a tertiary position? One. It can only be 1, right? Yeah. So even though it's 5.5 times, it's times 1. There's only 1 position, right? Okay. If we have triply substituted carbon, then the minimum number of hydrogens that can be there is 9. There'd be 3 methyls, right? Okay. So if we have 3 methyls here, on each one, how many primary hydrogens would there be? 9. So that reactivity of 1 happens 9 positions, doesn't it? Yep. Those are all the primaries. And so 9 times 1 is going to be 9 for the relative amount of reactions that will happen at that position. Okay? The tertiary hydrogen is a 5.5 for the relative amount of reactions that happen at that position. Okay? Okay, so when you do percentages, what do you always have to do? Well, it's a part divided by the total, right? So this would be part 9. Then we divide it by the total. The total being 9 plus 5.5, right? Multiply by 100, so we get a percentage. And that gives us 62%, doesn't it? Okay. Okay, so the tertiary position would be 5.5 divided by 9 plus 5.5, right? And that gives us 38%. So which position are we actually most likely to substitute? One of the primary positions, aren't we? 62% likelihood. Okay? So which product do we actually get more of? Primary position. Yep. 62% of our product should come out as primary position. Okay? So even though the tertiary are more stable, sometimes that happens because you just have more positions of the other states. Okay, let's look at some of the rate of substitution on the bromination of propane. So again, we have propane, it's reacting with bromine, again under the same reaction conditions, and what we see is that the bromine is only going to have 3% yield on the primary position, 97% yield on the secondary position. That boils down to a 0.5% per hydrogen on the primary, 48.5% hydrogen on the secondary position. Okay? So a far different result, right? Much more likely to get the secondary positions. Okay. Now, why is that? Well, this is partially due to the fact that we're no longer exothermic. We're actually endothermic. Okay? So we actually have to heat the bromine. Remember where I was saying that we actually have to heat this? Okay. Well, ta-da. That's what this says. Notice that the secondary radical again, we have the pretty similar energy differences. This is a 9 versus the 4 before, but this one's still around 10, right? But what's going to happen is we react, the primary position reacts much faster, but we can go backwards, can't we? See that? It's actually easier to go backwards than it is forwards. Okay? And the enthalpies tell us a slightly different story, doesn't it? Okay, so we have a faster reaction going to the secondary, but not that much faster. We have the ability to go backwards and forwards, and we have an exothermic, a slightly less energetically disfavorable product for our secondary radical, right? Okay. So this right here again ends up giving us a much more drastic separation between products. We have a lot more of the major products, secondary in this case, than the previous one where we did chlorine. Okay? Did I lose people? No? Okay. Okay, please do let me know if I lose you. Okay. So again, this is going to give us a Hammond postulate. Related species that are similar in energy are also similar in structure. The structure of the transition state will resemble the structure of the closest stable species. Endothermic reactions, the transition state resembles the product. Exothermic reactions, the transition state resembles the reactant. So this right here is actually going to demonstrate the Hammond postulate, actually. Okay, so in this case with the bromination, what energy difference are we closer to? The energy difference between the activation energy, the transition state, right here, is closest to the products, isn't it? And so according to the Hammond postulate, this transition state will most closely resemble the products, okay? When we're talking about reaction transition states, what we're talking about is, so when we do this reaction, right, what we have is we have a hydrogen coming off of something, right, propane, secondary or primary one, a bromine free radicals coming in, that's pulling an electron into a bond, and at the transition state, you'll have two bonds that are forming to that hydrogen, and two bonds that could possibly be broken, right? That hydrogen will be moving into a space where it's starting to break a bond with the carbon, it's starting to make a bond with the bromine. Does that kind of make sense? Okay, that's the picture. That make more sense? Fantastic. See these dotted lines? Those are bonds that are breaking and forming. At this state, this could fall in either direction, okay? Once you're in this transition state, this can go back to reactants, in which case we see no observable change, right? Or it can go to products, in which case we get product, okay? If your products stay around in the system, this could go backwards as well. But for many reactions, we play a trick. We have one of the products as a gas, and so that escapes and we can't go backwards. Okay? Or we do similar things. Okay, so in the Hammond postulate, the energy difference between the transition state and the products is closer. And so look at and see how this hydrogen is closer to the bromine, right? It looks like it's completing that bromine-hydrogen bond, doesn't it? And then we have a larger separation between the hydrogen and carbon. That's the Hammond postulate. It looks more like the product, right? Okay. The Hammond postulate for the chlorine version, the reactants are close in energy to the transition state, right? And so what the postulate states is that your transition state, the hydrogen will be more like it's in a bond with the carbon, okay? It's less like it's a bond during the transition state with the chlorine. Is that making sense? Fantastic. We have the postulate. Are postulates facts? Are they laws? Postulates are theories, right? Okay. So keep that in mind. Theories are not perfect. Theories always have to be attempted to be disproven. Okay? So it isn't 100% always this way, but it gives you a pretty good rule, general rule of what would your transition state look like. Okay? Okay, so let's talk about radical inhibitors. These are going to be often added to food to retard spoilage by radical chain reactions. Without an inhibitor, then each initiation step will cause chain reactions so that many molecules would react. So let's say one of these initiation steps happen for a chain reaction, free radical chain reaction, similar to what we've been looking at, but probably not with chlorine. Okay? If that happened in a food, what would happen to the food? Basically, it would rapidly spoil until there's nothing left, right? Okay. So what can you do to stop that? What do you think an inhibitor means? Yeah, it's going to react that free radical way, right? So that it can't continue the chain reaction. Okay? Without it being a chain reaction, those aren't that problematic, right? You can't spoil the whole food from one event. Okay? So an inhibitor is going to combine with your free radical to form a stable molecule. You may be wondering, what are these amazing free radical inhibitors and how dangerous are they? Well, there's such things as vitamin E, vitamin C. These are actually some naturally forming free radical inhibitors. Your body uses them basically for the same purpose. Because if you have a free radical chain reaction that happens in your body, that can damage many, many DNA molecules, many proteins. You get the idea, right? Could be a big problem. And so vitamin E and C help to inhibit these free radical chain reactions. Yeah. And so we use those same things in food. So again, look at a chain reaction. In a chain reaction, you have many exothermic steps, right? And so what would stop a chain reaction? Basically nothing, right? Because you always make the energy for the next step, don't you? That's a problem. Unless it's a reaction you really want to happen, that's a big problem, right? So what do? Well, we add an inhibitor. The inhibitor binds so well to one of the intermediates in a chain reaction that the inhibitor then forms, and it is an endothermic step to go back and get the next step of the chain reaction. Okay? And so this is too stable. The next step would be endothermic. Now, that creates a very slow step, right? Because two things happen. Number one, thermodynamically, this would be favored, right? But as important, or probably more important, is actually the activation energy. See the activation energy? That's slow now, isn't it? In the previous cases, these activation energies were always small, easy to overcome, fast, right? Okay? This is extremely slow. In a food or biological situation, you don't have to stop reactions. All you have to do is make them slow. Okay? Because in food, you're going to eat it. There you go. That's why you use a fridge, isn't it? Okay? Like, you could stop the reactions by doing things like dehydrations and stuff, but it changes the food a lot and tastes bad. Or you could put it in a fridge, right? Lower the temperature. What does that do to the speed of reactions? Slows it down. Yeah, that's why you use a fridge. Okay? And a similar principle here. Biological, by the way, you aren't slowing it down so you can, eat it or something. Biologically, you slow it down so you can urinate or excrete it. Okay? Or grow new. Any which way. Anyways, that's how inhibitors work, and a lot of cases actually, not just food spoilage, but food spoilage was the example that was easiest. These are the reactive intermediates that we're oftentimes going to run into. This is something you guys should just memorize and understand really well, okay? If you have a good understanding, there's a lot less memorization that needs to go on. But these same reactive intermediates are going to show up for the rest of your organic career, for all of your biochemistry, and then they're going to be something that will pop up constantly in a medical career or any science career, okay? They're just something that will never go away because they're incredibly important. Okay, so the four major reactive intermediates of carbon that we have to think about. I'll start with the one in the middle that we've already seen a lot of at this point. That is radical, right? Okay, so we have a carbon radical. Yeah, you're on mine. Okay, so that's the carbon radical we've talked about many, many times by now, right? Okay, this right here is called a carbocation. Guess what it is? Cation. Yeah, so it's going to be positively charged, right? Okay, this right here is a carbanion. Everybody say it with me. Carbanion. Yeah. Okay? Carb, anion. Carbanion. Right. This right here is then a carbene. So carbanion, negatively charged with a lone pair, right? Carbene is going to be a neutral lone pair carbon. Okay? You can think of it sort of as the result of two dissociations. Right? It's lost two hydrogens and kept one electron from each. those electrons can pair up, so they're not necessarily a free radical anymore. Okay? Okay, so again, highly reactive. They're reactive intermediates. These are going to be short-lived species. You typically cannot isolate these. They're not something that you're going to buy off a store shelf. Okay? You can't go like Sigma Aldrich, give me some carbene. Okay? That's not what happens. There's something that's going to be made in situ. Do you know what in situ means? In place, in system. Okay. And then used in that system. They're short-lived, meaning that they're made and then immediately impact into something and react with it. Okay? They're never going to be present in high concentrations because as soon as they react, they're going to react with something. Okay? Whether that is with the same things they just formed from, in which case you get back your reactants, or whether that's with something else and you get products. Okay? They're reacting with something almost immediately. Okay, so let's look at the structures. This will actually make sense then of why the forms that are stable are stable. Okay? For example, I promised you that the free radical, we're going to talk why the secondary is more stable than primary, tertiary is more stable than secondary. This is going to go in that. Okay, so this is the top view and side view of a carbocation. So when you have a carbocation, what happened? Well, it lost 2 electrons, didn't it? It lost 1 electron that would have been in the bond from the other thing, and then it lost 1 of its own electrons as well. Okay? This typically happens when something like a chlorine, iodine, something like that, comes off and takes the electrons with it. Okay? It's a heterolytic dissociation. Everybody remember that? Okay. This gives you a positively charged carbon. This means you have 3 sets of electrons, 3 bonds that are still associated with it, right? What's the maximum separation for 3 things? Trigonal planar, right? This shape is trigonal planar. Yeah, because that's the maximum separation for 3 electron domains, right? Remember, there is no electrons in this p orbital here, okay? It's lost 2 of the electrons that would make the 8 electron octet, right? Or another way of saying that, it only has 3 sets of 2, right? Okay. So what's going to happen with a carbocation is that it's going to have a vacant empty p orbital. That vacant empty p orbital doesn't actually take up any space per se. It doesn't cause these sigma bonds, this electron domains here, to be pushed any direction because it's empty, right? Doesn't have electrostatic interactions. Doesn't have a negative charge. It's in fact positive. Okay. This can also be called carbonium ion or carbenium ion. Those are 2 other names for this that you'll commonly see. Okay. This is sp2 hybridized. Why is it sp2 hybridized? What's hybridization mean? So we're making a single bond. That means we're using the s, which is direct overlap, right? We're also then using 2 p orbitals, which gives us 3 orbitals to make the bonds with, right? Okay. The 4th, which would be another p orbital, this is vacant, open, and free right here, right? Not involved in hybridization. Okay? Okay. Anybody have any questions so far? Did I lose anybody yet? Fantastic. Okay. What does this mean? Well, we have stability of order stability is going to be the most stable carbocations are going to be the most substituted ones. So the tertiary are the most stable. The secondary are the next most stable. primary, less stable, and then if you have a methyl, that would be the least stable. Okay? There's actually two different reasons for this. So there's the inductive effect and then the hyperconjugation. Okay? Okay. So the inductive effects is going to be the donation of electron density that's going to be donated along the sigma bonds. Remember, sigma bonds are the overlapping single bond structure we're used to. Okay? It's where it has the direct overlap, right? So remember, when you have these carbons with hydrogens around them, the hydrogens actually allowed the carbon to take on a little bit of its electron density, right? And so these carbons are actually just a little negative, right? They have a little bit of extra electron density. Now, what's going to happen is when you have a carbocation, that center carbon is now positive, isn't it? And so that's going to pull electron density from those CH3s. And that's going to happen directly through the sigma bond. It's going to pull the electrons in the sigma bond towards it because it's more stable that way, right? And the methyls have a little extra negative charge to counteract that, so it's fine. Okay? Did that make sense? Okay. Kind of like if you had people connected by ropes, the people on the outside have slack, the person in the middle is getting stretched. What would you all do? Person in the middle pull a little slack from the people on the outside, right? And make a more stable structure. Okay? Okay, so the second one would be hyperconjugation. This is going to be the overlap of the sigma bond orbitals with your empty p orbital. So remember, this empty p orbital's straight up and above and below the plane of the carbon, right? So this right here is one of the methyls we're looking at, and this right here is then the carbocation. Notice that the sigma bond sp3 hybridized orbitals actually somewhat overlap with that empty p orbital. See that? And they do it in a way that's pretty similar to a pp overlap that we looked at for pi bonding, right? Okay? See that? So we sort of form this small amount of overlap where it can pull electron density, pull the electrons a bit closer to it, and that's going to stabilize that positive charge. Okay? Is that making sense? Okay. And that's hyperconjugation. Remember that the pi bonds are conjugated bonds, right? So literally hyper above conjugation. Joining, above joining. Okay, that making sense so far? Okay. Anybody have any questions about that? Because we're going to reuse those same terminology and same concepts later on. Okay? Okay, fantastic. Okay, so let's talk about unsaturated carbocations real quick. The unsaturated carbocations are also going to be stabilized by one more factor, and that would be resonance stabilization. So remember, when we have a carbocation, what do we have? We have an empty p orbital and a positive charge, right? What happens to be located in p orbitals? I talked about it in hyperconjugation. P orbitals are overlapping, pi bonds are overlapping p orbitals, right? So if you opened up another empty p orbital next to it, what do you think is going to happen to that electron density? Okay, I have a pool, and then I just take a shovel and whoop, empty out that side neck of the pool. What happens to the water? It's going to flow into that other one as well, right? Okay, because it's going to flow into the empty space, right? So when you have a carbocation next to a pi bond, i.e. a double or triple bond, the electron density will flow into that other p orbital area, okay? And so if you were actually looking at it, you'd end up with like 1.5 bonds for all of them, right? If you'd end up with 2 electrons flowing around 3 carbons. Okay? But because we can't really write that on paper, what do? We do a resonance system, right? Okay. We're going to write out Kekulé structures, which are the individual structures in this resonance. Okay? And so we write a resonance forms. One has a double bond, and we put the carbocation next to it. And then we have a resonance structure where the electrons in the double bond go into a double bond with the carbocation, right? And that leaves the carbocation on the other carbon. We put a little double arrow between them, put brackets around them. Congratulations, we now have made resonance forms, the sum of which would give us our actual structure, right? Which is that all 3 carbons share those electrons, okay? You end up with partial positive charges on the outer carbons because the middle one, the electrons are always somewhere in there, right? Because the 2 are pulling the electrons across, meaning the middle one kind of gets the benefits. Yeah. Kind of like when 2 countries argue. The middle one always gets the benefits, right? Yeah. Okay. Anybody have any questions about this so far? Can you see that's just a very natural consequence of opening an empty spot next to delocalized electrons of any sort, right? If you had any delocalized electrons that would overlap at all, they would flow into an empty spot. Okay. Very good. So this is the most common, is we'll see that in unsaturated carbocations, stuff with double and triple bonds. That's the most common ones, okay? But we will get it in some other stuff as well, and we'll talk about those when they pop up. I just want you to understand that that's not just like a niche thing that doesn't exist everywhere else in life. Okay. So these are free radicals right here. And notice the free radicals look a bit like what? They have a p orbital. It's not quite full, is it? So what are the free radicals a bit like? So we had a p bond that was empty, and that was a carbocation, right? We have a p orbital that is now only half full. They're similar, aren't they? Yeah. So free radicals are in many ways going to act like carbocations, okay? Empty p orbital, it's not filled, so it can end up pulling stuff into it, okay? And so again, this is the top-down view. This is the side view. Again, we see the empty p orbital that doesn't have it completely full here. It's not completely empty either. It has 1 electron in it. That's that odd electron that we call this a free radical for, okay? This is going to, again, be stabilized by alkyl substitutions, just like the carbocations. Remember the order of stability for carbocations? Exact same for free radicals, okay? Because, again, it has the same things that will stabilize it. What could stabilize an empty p orbital? Well, we could get a little bit of inductive effect, pulling the electrons closer from the sigma bonds around it. We could also get hyperconjugation, pulling electrons in from the bonds that overlap it above and below the ring, right? Okay. Or above and below the structure. In this case, not ring. By the way, can I ask you guys a question? So, I want you to do a little critical thinking real quick. You look at this right here. It's an empty orbital. It has a positive charge. It's pulling electrons in from this other bond. Why doesn't that bond just get pulled over? Like, you have 2 bottles there of drinking. He's dying of thirst. If you went ahead and shared it a little bit and let him have a drink or 2, what keeps that from just sort of moving over time? Well, you'd probably complain, right? You'd probably say no. No stealing my liquid, right? But these are inanimate objects. They're not going to smack each other, are they? So there isn't anything, is there? You think that's a possibility, maybe? Can you see that the electrons are literally getting pulled over and you could form a new bond, right? Oh my goodness. Do you think perhaps these unstable intermediates could cause changes in structures? Yeah, maybe, huh? Yeah. Can you see how that might happen? Okay. So, whenever I teach you guys this base layer to understand everything above it, there's a lot of this that you could just derive yourself. Okay? Like a lot of this you could just come up with your own information, own understanding. Okay? Okay, so this is the unsaturated radicals. It's very similar again to the carbocations. Remember again, you have this partially empty p orbital. It has now opened up next to a overlapping p orbitals for a pi bond, right? So what's going to happen to that electron density again? It's going to flow into the partially empty p orbital, right? In this case, though, we don't end up with partial positive charges. We just end up with partially empty orbitals on both sides. Okay? Okay. They both never end up filled. Does that make sense? And so you end up with free radical character on both of the ending primary carbons. Okay. Does anybody have any questions? No? Man, you got real serious when I suggested stealing your water bottle. No, I got it easy. Yeah. Man, this would have caused real problems if I had said the Gatorade. Sorry, I just have to tease you guys a little. Okay, so this is the carbanions. The carbanions are going to have a filled orbital, right? And so this is going to be a lone pair instead of something with a bond. That means it's still going to be tetrahedral. It's a filled orbital, right? It's still a domain that's going to push everything else away from it. You still have four objects that are trying to separate themselves the most they can in space, right? Because they repel. And so you end up with tetrahedral, still have electrons on that carbon. You are going to have a negative charge on the carbon. The carbanions, need more water, are nucleophilic and they are basic. Those are slightly different things. Nucleophile means it does what? Likes positive charge, right? So it's going to attack positive charges and try to bond to them. Literally, something's going to try to come on here and make a bond, right? And they're basic as well. Basic meaning that accepts an H+, right? Similar, but not the same. Okay? Okay, we'll go ahead and pick up... well, no, we could finish. Let's do the stability of carbanions, then we'll finish. Oh, I have the wrong diagram anyways, don't I? Okay. I'll replace that diagram, and we can start on here. How the hell is that still the wrong diagram?